Let's start with a short background. Automatic program repair is a technique that automatically fixes software's bug. In general, it consists of 3 steps. First, it takes a bug program and its specification, such as test case, as input. Second, a patch generator produces candidate patches by modifying the original programs. Third, it runs the test and returns the patches that pass all the test cases. However, in APR, there is a serious problem called overfitting. It means that the system generates patches that only pass the given test, but still remain some bugs. This problem makes APR less effective because the system may generate some incorrect patches, which lower the repair performance, and it also makes APR unreliable since users cannot fully trust the patched program. So, to resolve this problem, recent works have proposed automated patch classification techniques. The key idea is to automatically detect and remove incorrect patches before they are delivered to users. By pruning those incorrect patches early, it can improve the overall repair performance and reduce manual effort required to find the correct patch. However, we found that the existing techniques significantly reduce the performance of APR when they combined with real systems. For example, when we apply the existing technique to a real APR T-bar, they effectively prune out many incorrect patches, but they also removed many correct patches. As a result, they dropped T-bar's fix rate by about 50%. Then, why does this happen? Let's see what we usually expect when using APC. Here's the large box is the total patches generated by APR, and the smaller box inside shows the plausible patches that pass all the test cases. Then, normally, we expect that there are a fair number of correct patches, like the circle here. So in this case, even the classifier accidentally removes a few correct patches, we still expect it to be helpful because it removes much more incorrect patches and improves the overall performance. However, in practice, the number of correct patches is extremely small, so even smaller than this tiny dot. So in this case, if the classifier makes a small mistake, it can easily prune out all the correct patches, and the APR will fail to find the right fix. So the key point is that in APC, preserving the correct patches is essential. If not, it can actually reduce the performance of APR. Now let me show you our motivating examples. These are the patches generated by the actual APR systems. The left one is the only correct patches for the chart 1 bugs, and the right one is incorrect patches for the other bug. And we found that all the existing techniques fail to preserve the correct code on the left. For example, ODS, the syntax-based method, misclassifies the correct patch as incorrect because its null handling code looks similar to the other incorrect code. Patch-sim, the execution-based method, also labels it as incorrect because the patches significantly change the behavior of the passing test cases. Unlike the previous method, our technique Prism focuses on semantic changes introduced by the patches. For example, let's look at the correct code on the left. Before the patch, the code skipped the return statement when the data set is null. Then, since the data set is null, an NP can occur in the next line. After the patch, when the data set is null, the code executes the return statement. So as a result, the data set becomes non-null in the next line, so no NP occurs. In this way, Prism represents this patch as eliminating an NPE. Now look at the incorrect patch in a similar way. Before the patch, the MASD is non-null, so no NP occurs. And the method returns either the mean value or the null value. However, after the patch, the MASD becomes null, so an NP cannot occur. And the method always returns null value, which means that it becomes a constant method. As a result, Prism summarized this patch that it creates an NP and makes the constant method. Then based on this summarization, Prism distinguishes the patches by the presence of an MP and constant method. This is the overall workflow of Prism. It takes the original buggy program and patched program as input. Then it analyzes both the programs separately. Next, it compares the alarms reported by the static analyzer and represents the patch as semantic feature vector. Finally, using a learned formula trained on the label data set, Prism classifies the patch as correct or incorrect. Now, I briefly introduce the two key ideas of Prism, the semantic feature and the learning algorithm. For semantic feature, we use changes in static analysis alarm. More specifically, we represent each alarm's generation and removal and preservation as semantic features. For example, let's look at the correct code in the previous example. Assume that our analyzer extracts a set of used variables and NP expression. Then the analysis ledger before and after patch look like this. Then, by comparing these two ledgers, we can see that the set of used variables is preserved and the NP expression is removed. So we can represent this patch with a feature vector that says used variables are preserved and NP expressions are removed. In this work, we use the changes in 11 semantic properties, and these features are grouped into 3 categories. First, definition and use of the function and variables. Second, values in the memory state. And third, exception. We designed the customized static analyzer to extract each patch and each feature, and the definition of our abstract domain and design choice for each feature, and the key ideas for sound and precise and scalable analysis as described in our paper in detail. Next, I'll explain the learning algorithm. Our learning algorithm aims to find a Boolean formula that preserves a sufficient number of correct patches while detecting as many incorrect patches as possible. More specifically, it constructs a Boolean formula that describes the correct patches. It starts from the atomic feature and gradually builds more complex formula. First, it chooses some candidates from the entire set and specifies them. This means that it conjoins the original formula to make a new one that represents a smaller set. Then, as a ledger, the number of correct patches detected by the formula monotonically decreases, while the number of correct patches monotonically decreases. So thanks to this property, we can safely prune out the formula that does not satisfy the given threshold. Next, the algorithm chooses some candidates again and generalizes them. This means it disjoins the formula to represent a larger set. And as a ledger, the generated formula covers more correct patches and fewer incorrect patches than before. And thanks to this property, the algorithm can explore more candidate formula again. Our algorithm repeats this process within a given time budget and returns the formula that detects incorrect patch most effectively. Now let's move on our evaluation. In this presentation, I focus on 2 main experiments. First, we evaluate the performance of Prism when it is combined with real APR systems. To see whether Prism can improve the APR's performance, we use the linked patch data from 10 APR systems. Second, we evaluate the overfitting detection performance of Prism. This experiment was conducted on labeled data set from the previous studies. Here are the ledgers of the first experiment. It shows that only Prism achieved the both goals, improving APR performance and reducing the review effort. The other techniques could reduce the number of reviews by classifying many patches as incorrect, but they also remove many correct patches and lower the overall performance of APR. In contrast, Prism finds 9 more correct patches while requiring 72 fewer reviews than baseline. And in our paper, we also report detailed ledger for all 10 APR systems, so please check it out if you are interested. Next, here are the ledgers of the second experiment. In this experiment, to ensure a fair comparison, we compared overfitting detection performance under the same correct patch preservation rate. As a ledger, Prism consistently outperforms all other techniques across all preservation levels. And in this graph, you can see that the patch sim only appears at 75 point because it can preserve correct patches only in the specific range. Similarly, in the paper, we compare the performance across all preservation levels in details. So this is the end of my talk. In this work, we developed a technique that automatically classifies patches to address the overfitting problem in APR. The key challenge is that APR performance can only improve when we preserve as many correct patches as possible while detecting many incorrect patches. To achieve this, we proposed Prism, a semantic-based approach to patch classification. Our technique has two key main ideas. First, it represents patch using new type of semantic features. And second, it learns a Boolean formula with high accuracy. Thank you for listening to my talk.
Is there any question from the audience? Please go to the stage.
Hello, thanks for the talk. So we know that static analysis may over-approximate program which may create false positives. So I'm curious how the different levels of abstraction of static analysis in Prism affect the overall performance of Prism on fixing the APR.
Okay, that's a good question. As you said, static analysis is basically sound, so it can make some spurious alarm, which means that the behavior is not actually in the real execution. So to handle the case, we extract the features only the only the case for non-top values are related. It means that we extract a feature that definitely true case in true case.
Okay, so which level of abstraction do you use in your static analysis components?
We use a simple flat domain and lift the value to top when merge appeared.
Okay. Okay, thanks.
While we wait for the audience to come up with more questions, I do have one other question. So have you tried using like large language models to do the same problem, and do you know how well they will do compared to your technique?
Actually, I cannot consider the large language models, but I know that there is a recent work that using the large language model, but I found that it also has the similar problem that it aggressively prune out the correct patches, so it may be degrade the performance of APR.
Okay, thanks.
Thank you.
Are there any other questions from the audience? Oh, I have another question. So have you tried applying your tool to some like realistic code bases and patches? Like, I'm assuming that there are many like GitHub patches. Have you tried?
No, I'm not.
No, okay, it's fine, thanks.